All right. Now we're going to talk about the gravitational force in the case where we're not close to Earth's surface. So, when close to Earth's surface, we've been using this approximation that there's a uniform gravitational field, 10 newtons per kilogram, directly downwards. But in actuality, the gravitational field strength, which is the force per unit mass, is actually given by a more fundamental expression. Now, we'll talk about where this comes from when we connect it back to force shortly. But this is known as Newton's law of universal gravitation. It determines sort of what field a given point mass is producing. So any object with mass will produce a gravitational field a distance r away given by big G times m divided by r squared. So this constant is known as big G, and it is not planet specific. This is a constant of the universe. And it has these nasty units, and it's approximately 6.67 times 10 to the minus 11. And this is not a derivable constant. This is something that is just known in our universe. So the gravitational force is purely attractive, and this field falls off quadratically with distance. So as a result, the field is decreasing as you get farther and farther out. So masses are sinks for gravitational field lines because they are sort of uh, all the field lines are sort of going into this mass, and we see they get longer and longer when we're closer to the mass. So the farther you are away, the less pull you feel towards that mass. And if there's multiple masses, the net field can be found just by adding all these vectors together. So first, let's make sure that we do get the result we expect out of this formula. So given that the mass of the Earth is that and the radius of the Earth is that, verify that the more precise gravitational field expression yields the expected result near Earth's surface. So we know that near Earth's surface, the expected G value is 9.81 meters per second squared, or sorry, I should say newtons per kilogram, although they are the same. So our expression for little g is that little g at a point is the universal gravitation constant times the mass of the object divided by the squared distance from the object center. So near the surface of the Earth, we can just plug in Earth's radius. So we do all our plugging and chugging. You can check the units work out, but it's kind of a mess. So this is literally just a calculator exercise. So again, you know my opinion on numbers. So there must be something important by actually doing this. And of course there is, because this is a well-known result that we've been using for G. So let's see what it is. Enter Desmos and look at that. So I did this so you'd actually believe me and not just take my word for it. So I typed this into the Desmos box and we get 9.81 meters per second squared, or newtons per kilogram. So 9.81 newtons per kilogram, which is exactly what we expect. That is our very well-known G value. So now that we know that this at least gives us the expected results, let's just do some work with the G field. So we have two asteroids. Asteroid 1 has mass 1m and asteroid 2 has mass 4m. And we want to draw first some vectors representing each of the fields at d over 2 at the midpoint. So we know that each of these masses are going to be sinks. So the mass m would generate a field sort of like this. The mass 4m would generate a bigger field that's like this because it's larger. So we can see the fact that there's 4 tick marks makes it really appropriate to just use a 1:4 ratio here. So the field from mass 1m at the midpoint, we'll just give that 1 leftward unit, because the mass 1m would try to pull masses towards it. And the field from the 4m mass at the middle, well, it's the same distance as the other field, but it's 4 times as massive, so we get 4 times the field towards the 4m, so the net gravitational field would be 4 minus 1, which is 3. And we'll see that idea sort of come up in the next part. So the net gravitational field is towards the heavier mass, which makes sense, because you're getting pulled towards the little m and getting pulled towards the big M, but of course the bigger mass wins when the distance is the same. What is the net gravitational field strength at d over 2? Well, we said that we can do this by vectors. So it's going to be the field generated by the m as a vector plus field generated by the 4m as a vector. So our expression for g is gm over r squared. So we have a big G, we have a mass 1m. D over 2 is, of course, d over 2 from the first mass. And that gets squared in its entirety. And that field is directed, we said, to the left. You could use unit vectors as well if you want. You can call this negative I hat. And then we have a 4m field at the same distance away from its mass, directed to the right. That's bad. Okay. So now we got to do some algebra here. So be very careful when doing inverse square law stuff. Make sure you're squaring everything in the denominator. So if I square the entire denominator, I get d squared over 4. So just be careful of that. So d squared over 4. So if I do that, this becomes 4. So I essentially have 4 units left, and I have 4 times 4, which is 16. 16 units right. So this is essentially 4. This is essentially 16. So 16 minus 4, because they're competing, this would be 12 gm over d squared right. So also notice we do get that, like, that 4-to-1 ratio slash the net field of 3 here, right? Because notice the field from the left mass was essentially 4 gm over d squared. So our net field was 3 times that. And that's consistent with our force arrows, or field arrows, rather. There exists a location between the masses where the net gravitational field strength due to both masses is 0. Where is it? So where is the 0 field location? Is it closer to the little m or closer to the big M? Well, I usually like thinking about this problem as, again, the net field says which way you'll get pulled. So there will be a spot where a mass gets pulled towards neither mass. And we definitely know it's not going to be over here or over here, because the fields would add in those regions. So the fields are competing here. So we know the position exists because the field points to the left when I'm really close to this mass, and the field points to the right when I'm really close to this mass. So there must be a turning point. And where is that? Well, it's not the middle, because at the middle, the big field is winning. So it's not the exact middle. So what we have to do is we just have to shift a little bit closer to the little mass to account for that. Because if we're generating too big of a field at the middle to cancel, I need to increase the distance to artificially lower that. Because since the 4m has more mass, you must have to have more distance from that mass to generate the same field as the 1m. So in a lot simpler language, probably, here's my answer. For the gravitational field to be 0, the field from each mass must be equal magnitude, opposite in direction. Since the mass at x equals d is greater, a larger distance is required from this mass to account for that, right? The numerator gets bigger, so you got to make the denominator bigger to compensate to get the same field. All right, let's figure out where that field is. So this problem actually shows up a lot more in E&M than a mechanics context, but I really like this problem. I think it's a good skill builder here. So we're saying that there's a magic point x0. We're going to put like right here. such that the field is 0. So what we know, at this point x0, we know that g from the 1m is equal to g from the 4m, and I'm using magnitudes here. So g from the 1m is big G times big M divided by the distance x0 squared. Then we do the same thing for the 4m, except we got to figure out what the distance is. So think about segment addition. So we know that the entire separation between the two masses together is going to be d. So if I've already contributed x0 to the distance, this means the remaining distance must be d minus x0. There is a really clever ratio approach you can use for this. I think I'll let you discover that for yourself. No, I can't. I think I have to talk about it afterwards. It's too good not to share. This would be d minus x0 squared. All right, now we got to solve this for x0. So physics is done. Physics is done now. So we just got to do some algebra. Also, this isn't as bad as it looks because g and m cancel. So we get 1 over x0 squared is equal to 4 over d minus x0 all squared. And just to make things easier, notice that there's no pluses or minuses sort of attached to the ends of these terms. So we can actually, it's perfectly valid just to square root both sides. But I think we'll collect all the squared terms first. So I could write d minus x0 squared divided by x0 squared equals 4 if you cross multiply. So this means if I take a square root of both sides, this would mean d minus x0 over x0 equals plus or minus 2. I do actually have to do plus or minus because it could matter. So I get d minus x0 equals plus or minus 2x0. Let's see, do we need the plus or minus? No, we don't. We don't need the plus or minus. Almost any time in this class, you don't need the plus or minus. You could if you want to be pedantic, and you will see that it does not matter. You can take my word for it that we can just take the positive root. So d would be equal to 3x0, so x0 would be equal to 1/3 d. So I said there's a clever ratio approach to this because notice, like, that was a really ugly equation, but the answer we got was relatively simple, 1/3. So how could you have figured that out? Well, we know that g is proportional to the mass divided by the distance squared. So notice that mass 2 had 4 times the mass as mass 1. So if the numerator is 4 times, that means the denominator must also be 4 times. So for example, if the mass of the second object was 4 times, to generate the same field, our radius, or our distance, I shouldn't call it radius, our distance should have been 2 to make that 2 squared equals 4. All that to say, this tells us that the distance from the large mass must have been exactly double. So this would be x and this would be 2x. So therefore, 3x equals d. You could get that without all this manipulating. All right, this was a mean question to ask in this section, but it's technically solvable. So if you know an idea from later in the course, you could do this a lot easier. But there's a nice way of doing it regardless. It says, suppose the asteroids are released from rest. Derive an expression for the position where the asteroids collide. So once again, we're just going to draw our little line here where we have our m and our 4m. So they're released from rest, and the only thing exerted on the asteroids are their mutual attraction, right? This m is going to pull the 4m towards it. The 4m is going to pull the 1m towards it. So the asteroids are moving together because of Newton's third law of forces, right? Equal yet opposite because they're interacting objects. So what we know is that our forces are going to have the same magnitude. So the force on the M is going to be the same as the force on the 4M. So we do know that there's the same sort of driving force in each of these situations. How does that help us know where they collide? Well, equal forces, not equal accelerations. So we know that the acceleration of the 4M is going to be a quarter of the acceleration of the 1M because net force divided by mass is acceleration. And that should make sense. So they are getting pulled the same amount with the same amount of force, but the 4M goes less distance or less acceleration under that because of its increased inertia. So all that to say, at any given time, this mass will be moving 4 times faster than this mass, which means that if we release them, this bulky mass isn't going to move very far because it's pretty heavy. So we know that the crash site is going to be somewhere much closer to the 4M. And actually, we can work it out directly because we know that this M will travel a distance. If this mass travels a distance x0, the 4M has only traveled a quarter of that, right? Because quadrupling the mass quarters the acceleration. So we know that x0 plus 1/4 x0 is equal to their separation d. So 5/4 x0 is equal to d, which means that x0 is equal to 4/5 d. And that should make sense because we end up 4 times closer to the starting point of the 4M mass. Now, this is a very special quantity for this system, which we'll discover is called the center of mass. And there is an easier way of getting this result. I honestly think I made a mistake and forgot I didn't do center of mass yet. So this was definitely a reach. This was a reach from me, but it's also some intuition as where they should collide. Notice there was no kinematics or anything. We just reasoned that same force and it's internal. So we just get this acceleration ratio of 1/4. Wow, that's kind of tricky. So now we're going to do some problems with the actual gravitational force. So recall that since Fg is equal to mg, we can recover the actual formula for the gravitational force between two objects by substituting in our more precise value of g. So this is known as Newton's law of gravitation, which describes the mutual gravitational force between any two objects with mass. So that is the only requirement for a gravitational force. It is two objects with mass. So these are obviously the masses. This is big G. This R is the center to center distance. Might not be the radius. That's more of a physics C thing, which we'll talk about next section. But realize that we are always just looking at center to center distance. This is not the radius. Center to center distance. So for example, if you have like actual spheres that are touching each other, you just pretend that they're dots at the center with all that mass and you locate that distance. The key property to know about gravitation is, first of all, the gravitational forces are always equal and opposite between objects. That's just a third law pair. And also, it's an inverse square law. So doubling the distance quarters the force because 1/2 squared is equal to 1/4. This is the property to know. Doubling the distance quarters the force. Notice they're always equal and opposite forces. Just doubling the distance quarters the result. All right, gravitational force between two masses at a certain moment in time is shown below. Draw the gravitational force under each of the following ratio questions. Okay. So notice that there's 1, 2, 3, 4 ticks of force there. And there's 1, 2, 3, 4 ticks of force there. Makes sense. They have to be equal and opposite because of Newton's third law. So these two objects are interacting with each other, so that these are absolutely going to be the same at all times. What happens if we double the separation? Well, our first law is gmm over r squared. And this is just a fact that's really easy to memorize, but we can derive it just as easy. If we double the separation, we double r, so we double the squaring term in the denominator. So this gets us 1/4. So instead of one force unit, we should have, instead of four force units, we should just have one. So one little baby force unit. What if mass 1 is doubled? Well, if mass 1 is doubled, we're doubling one of these m's and not the other. So this means the force is doubled. And the force is doubled from its original value on both masses because the force is equal and opposite. So I need 8 force units. And yep, I'm sure I made that grid exactly 8 units long for this reason. Both masses are doubled and the separation distance is doubled. So GMM over R squared. I double this mass, I double this mass, I double the separation, and I square that. Wow, that's a lot of 2's. So I get 4 on top, but I get a divide by 4, so I actually just get 1. So this does nothing. So this is just the original, where it was 4 units and 4 units. So we can see that this works. So we originally have 4 force units, and when it's quartered, we have 1 force unit. Doubling it gets 8, and doing nothing gets 4. So we do need to absolutely be comfortable with this. This is the most common type of reasoning question you'll get with gravitational force. All right, 3 masses are placed along a line as shown. Rank the magnitude of the gravitational force exerted on each mass. So there's a combination here. Justify your ranking, then we're going to do it and find them all. Okay. So I don't say qualitatively here. So we're totally free to just use kind of some numbers. And my suggestion here would be to kind of use a multiplier approach. So essentially, what's going to happen is mass 1 is going to get pulled to the right by mass 2, and it's going to get pulled to the right by mass 3. So the force we know is going to be GMM over R squared. So the force between mass 1 and mass 2 is going to be 1 times 2 divided by 1 squared. So this is essentially 2 force units. Then the force exerted on mass 1 by mass 3 would be 1 times 3 divided by 2 squared, which would be 3/4 of a force unit. Then we'll do mass 2. So mass 2 is going to get pulled to the left by mass 1, and it's going to get pulled to the right by mass 3. So equal and opposite forces, we know that that force on 2 by 1 is also 2. And then by mass 3, the force would be 2 times 3, which is 6, divided by 1, because their separation is 1. So divide by 1 squared, this is 6. All right. Then for our last, we can, I think, just use double symmetry here, right? Because we already found a lot of these forces. We have a force left from mass 1 and a force left from mass 2. So I've coded these using colors, by the way, if you couldn't tell. So mass 2, blue, mass 3 is green, and mass 1 is purple. So we know this will be a 6, and this will be a 3/4, just by symmetry. So this was F13, so this was, no, this was F12, so this was F21. This was F 1, 3. This was F, 3, 1. This was F, 2, 3. So this is F, 3, 2. So we can do our ranking here. So we see that our numbers, we're going to get 2 plus 3/4, which is going to be a little bit less than 3. We have 6 minus 2, which is 4. And we have 6 plus 3/4, which is basically 7. So it is just 1, 2, 3. Justify your ranking. See above. So we sort of did this with rankings here. And now we'll see all these numbers actually pop out when we find the net force on each of the objects. So we know that the net force on mass 1 is just going to be the net force from 2 and 3 combined as vectors. So it is GMM over R squared. So the force from mass 2, you see we get G times M times 2M divided by D squared, and this was right, plus G times M times 3M divided by 2D quantity squared, which is also right. So if we do our simplifying, this term is 2GM squared over D squared, and this term is 3 divided by 2 squared is 3/4. GM squared over D squared. So we end up getting 2 plus 3/4. So 2 is 8/4. So we get 11/4 GM squared over D squared, right? And then we'll go a bit quicker for the next two because we've sort of seen the process, see how this works. So notice that they are just going to be, notice the 2 and the 3/4 shows up exactly here, right? That's why we do the multiplier approach. It makes the actual math a lot easier. So for mass 2, we said we are going to get 2 GM squared over D squared left plus 6 GM squared over D squared right, which gives 4 GM squared over D squared, right? And then lastly, we have 3/4 and 6. So we get 3/4 GM squared over D squared left plus 6 GM squared over D squared left. 6 is 24/4, so we get 27 over 4 GM squared over D squared. So doing all that work up front with our I call it like the substituting 1 approach. Where we just figured out the relative sizes of the forces. That really saved us a lot of time because really we were just crunching the same numbers with symbols. So we see that our forces were 2 plus 3/4 in front, which was 11/4. We had 6 minus 2, which was 4 in front. And then we had 6 plus 3/4, those are 27/4. And notice these numbers are increasing, right? 11/4 is less than 3. Then we have 4, and then we have 27/4, which is a little bit less than 7. So this is another big application, is I put this section off till the end so that we could access orbits and talk about circular motion. So you don't actually have to know Kepler's first or second law for these classes, but there's a lot of orbits that are possible. We're going to usually restrict ourselves to the cases of elliptical orbits. So any closed orbit follows an oval shape, but The math can get complicated at arbitrary points there, so we really like circular orbits, which is a simpler case of an ellipse. So when an object is in circular orbit, this means the orbital distance r is constant, so the centripetal force is constant, so the speed is constant. So circular orbits represent uniform circular motion, meaning everything we learned last time applies. So given the fact that centripetal acceleration and force depends on speed, it turns out there is exactly one speed that keeps you in circular orbit, at a certain radius. So that's why we don't actually see circular orbits in the real world, because you'd need one special speed. And if you miss it even by a little bit, you become an oval. So this is our general picture of a circular orbit. So we have a bit of an interesting QQT type design here I made for this one. This is the only time I actually did this, because we're trying to figure out, the question asks us to figure out the dependence of orbital distance, orbital speed on orbital distance. So we're going to put a satellite in two different orbits, and we're trying to figure out which orbit requires a larger speed to be in. So does the satellite orbit faster in orbit 1 or faster in orbit 2? So what I did, instead of making you pick instantly, because it's not super easy to reason through actually, is I gave you both possibilities. I'm telling you it's not the same. Student A thinks that you need a bigger speed for one. Student B thinks you need a larger speed for two. And assuming they're not just thinking randomly or guessing, like, what might their reasoning be? Now, of course, one of them will be right and one of them will be wrong, but what could their reasoning be? Error analysis is usually a good teaching tool. So we know for sure that these are in a circle. So the equation F perpendicular equals mv squared over r applies. So what might these students be thinking about? So student A argues that a larger speed is needed in orbit 1. What might they use to justify this claim? Well, student 1 might say that if the speed is larger in orbit 1, that's because if you look at the gravitational force is gmm over r squared. So what student A would correctly notice is that if you increase the radius of the orbit, you decrease the gravitational force. So student A might argue, if for a larger orbit, you need a lower force, you need a lower centripetal force. Thus, you don't have to go as fast. So they'll say the force exerted is greater in orbit 1, so the satellite in orbit 1 is getting pulled harder. And if it's getting pulled harder, it must be going faster. So that's what they might say. But student B might think the speed is larger in orbit 2. So what might they say? Well, student B, they might say, they might just look at the centripetal force equation. So what might they say? Well, student B might say something like, satellite B is farther away, so gravity's weaker there. And since the gravitational force is weaker, you might need a greater speed to keep it from falling inward. Because again, here we have an increasing radius. So student B might look at this increasing radius and say, well, if my distance increases here, I would have to increase my force here. So I'd have to increase my speed here to maintain a given force. So they might look at that. Now, one of these might look like a more secure argument than the other, but it's okay. It's just part of the task. So let's drive an expression for the orbital speed and see who is correct. Well, it's the same thing that we always do when we're a circle. So who's causing the circular motion? Well, it is, of course, the gravitational force. Now, we'll always model these as like one of the objects is much, much larger than the other, so that we can model the central body, is what we'll call this thing, is stationary. So we will say that the perpendicular net force is supplied by the gravitational force. And we are doing the satellite. So the net force on the satellite, do I give the mass of the satellite? I don't. Let's say the satellite has mass little m. V squared over r equals gmm divided by r squared. So notice the mass of the orbiting body is the one that cancels. So we're given, and one of the r's will cancel. So we're given v squared equals gm over r. So v would be equal to square root gm over r. So which student is correct? Justify your answer. Well, we see that as the orbital radius r increases, v decreases. So this means student A. So again, where did student B go wrong? Well, student B went wrong trying to argue that the centripetal force stayed the same. So student B forgot to link the fact that the centripetal force is supplied by gravitational force, which is decreasing. So student B could argue that yes, it's true that a larger speed is needed at a larger radius if the force is constant, but it's not. So they missed the linking variable there. All right, we'll conclude with a important application. This is the law of Kepler you need to know, which is Kepler's third law. I would not say memorize it, but you do need to be able to recreate this derivation from scratch. So this is about connecting orbital period to how far to the orbital radius. So what's an expression for the period of an object in uniform circular motion? Well, uniform circular motion means constant speed. So distance equals speed times time. And if we're in a circle, distance is 2 pi r. So the orbital period of a satellite or anything in circular orbit is 2 pi r divided by v. So just because this is a standard derivation, I'm having you redo the one from last time. Derive an expression for the speed of an object in circular orbit of radius r about a mass m. Yes, this is exactly the same. It's just super important, and it helps with the flow to make you redo it. So we said the radial centripetal force is being supplied by the gravitational force. So mv squared over r on the orbiting body is equal to big G times the product of the masses divided by the square of the radii. And we can just trust that algebra hasn't changed between now and the last page, so we get this expression again. Now we'll derive what's called Kepler's second or third law, which is not an expression for t, but it's an expression for t squared, is usually how it's written. So let's derive an expression for t squared. So we said that t is equal to 2 pi r divided by v. And we want t squared. So t squared would be 2 pi r over v all squared. So t squared would be equal to 4 pi squared r squared. Don't forget to square the pi. Divided by v squared. And that's going to be equal to 4 pi squared over r, 4 pi squared r squared divided by, well, v is gm over r under a root, so v squared would be that square root squared, so we get rid of the root. So this r can swing up to the numerator, because if we do our fraction arithmetic, this would be 4 pi squared r squared times r divided by gm. So we'd get t squared is equal to 4 pi squared over gm times r cubed. And this is known as Kepler's third law. And what it states is that an object's orbital period in a circle, although it works for ellipses too, with a slight modification, orbital period squared is proportional to orbital distance cubed. Because all of these things are constants in front. Yes, there is a mass in the denominator, but this is the mass of the thing being orbited. So this number is actually a constant for everything in the same solar system or orbital system. So every satellite around Earth will follow this law using M Earth. Every planet in the solar system will follow this law or about the sun with mass of the sun. So we're going to end with a little linearization where we try to calculate the mass of the sun. So we're going to approximate the orbit of each planet as circular, which is not terrible. Not a terrible thing to do. We'll see that they're pretty circular, even though they are ellipses, except for Mercury is a pretty notable outlier. So what is a set of quantities that we can use to determine the mass m of the sun? So if you're linearizing with planets, it's probably Kepler's third law. Like, this is a very important thing. So Kepler's third law states t squared equals 4 pi squared over gm times r cubed. So what can we plot to make this linear? Well, the t is being squared, so that's not linear, so that goes in the box. The r cubed is definitely not linear, so that can go in the box. So therefore, my number in front is just my slope. So that would be our linearization. There's like a million Kepler's third law linearizations you can do. You could also graph t versus r to the 3 halves, and you get some slope that's square rooted. But again, I do not like square roots. All right. Yeah, these are huge numbers because I use the actual ones here. So you can be sure we're definitely mining off camera for this one. Here's what I got. So I cubed my radii and I squared my periods, and it did make a very straight line. Actually, this line was so straight that when I did Desmos, there was no y-intercept. So according to our model, our best fit slope is equal to 4 pi squared over big G times m, which means that m times the slope is equal to 4 pi squared over G. So the mass of the sun is equal to 4 pi squared over G times slope, which is 4 pi squared divided by big G divided by the slope. We see we're going to get a very large answer, right? Because we're dividing by 10 to the negative 11th times 10 to the negative 19th. And this arrow is going to bother me. If we do this, we can trust my calculator here. If I was smart, I would have had this pre-fired into the calculator. Let's check my calculator history. I promise it's in here. 2.06 times 10 to the 30 kilograms. Not 13, 30. And that's actually not too far off. I think the actual mass is like 1.99 times 10 to the 30, something like that. So pretty good linearization. And I did use actual numbers for this. That's why they're quite bad. So again, I used actual numbers because I thought the real result was better here. All right, that is universal gravitation.